Hi there. Let me take a few minutes and take you through the solution rubric for this number 6 investigative task where essentially you're doing a test for variability. So parts A and B in terms of the scoring, they are combined together. So it's important that you define your parameter. So sigma squared represents the variance of the thermostats in degrees Fahrenheit. So you need to state your hypotheses just like we would state hypotheses if this were a test for means or for proportions. Indeed, what makes this an investigative task style question is that we don't typically do tests for variance in AP statistics, but it's set up just like any other test. So our null hypothesis would be that that variance is equal to 1.52. And we're looking for evidence that for one reason or another, the thermostats now have more variability in them, so greater than 1.52. So, and then calculating the test statistic, literally the formula is given to you in the statement of the problem. So in the statement of the problem, you are given this expression here. So you should enter the data, the 10 observations, you should enter them into your calculator and then find the sample standard deviation using one variable statistics. You can use that and you should show your work in order to calculate the statistic. So the sample size is 10, 10 minus 1 is 9, there's your degrees of freedom. That sample standard deviation is 1.43, so you need to square it. And then you have to divide by what we were given in the null hypothesis. That value of the variance is 1.52. Notice that 1.52 value is already squared. Don't square that. So then calculating that to be approximately 12.11, there is the second component. So writing the hypotheses and actually calculating the test statistic, that comprises one of the 4 components for this question. If you do one of the 2 correctly, this is a partially correct answer. Otherwise, it's incorrect. So for the next component, in part C, understand you didn't have to state any of the conditions. I said that assuming that the conditions for inference are met, this isn't a test that we've studied, so we wouldn't expect you to check the conditions here. Understand, be careful. If you try to, quote, check conditions and you state something that is incorrect, you will lose credit here, so be careful. What's important in this question then is you need to state a p-value and then you need to write a conclusion in context, and it needs to be listed or linked to that p-value. So in order to do this, I used the chi-squared CDF command on my calculator. So there are 9 degrees of freedom. The statistic we had was 12.11. So let me take a second and review how to do that. Going to the calculator, second distributions. We'll take a second. I can't remember what the hotkey number is, so I got to press the number down there. Oh, of course it's 8. There's the chi-squared CDF command. So my lower boundary is going to be the 12.11. The upper boundary, you should put in a large number. I'll put in 1,000. That should be plenty good. The degrees of freedom are 10 minus 1, or 9 in this case. That's given to you in the statement of the problem. So here's the p-value, 0.207. So that needs to be calculated and stated somewhere in the problem. That is one component of this question. But then in context, just like every other test we've interpreted, you need to link your interpretation and your conclusion to that p-value. That's the second component of this question. So with this p-value, which is greater than 0.05, we cannot reject the null hypothesis. So we do not have enough evidence to suggest that the variance of the thermostat temperatures is greater than the 1.52 degrees Fahrenheit. So calculating the p-value and interpreting in context, linking back to that p-value, both of those are required for another essentially correct component. If you only calculate the p-value, you have a partially correct answer. So otherwise it's incorrect. So D and E are combined into one component here. All you're doing is essentially marking the graphs that were given to you on the question. So in this part of the question then, you have to identify the critical value. So again, what is the value where 5% of the area in the chi-squared distribution will lie above it? Of course, you have to remember that we're using 9 degrees of freedom. So we don't have an inverse chi-squared command that would help you find that. I suppose you could guess and check it, although this is a good example of one of the few times where the tables that are in the back of your test booklet can be really quite helpful. So something to think about, table A is standard normal probabilities. We've calculated this either using the shade norm command or using the normal CDF command. This table here, table A, I'm not convinced that that table would be of much help to you. Here's the second part of table A. So if you continue on, the next table says table B, the t distribution for critical values. And again, we have a tcdf command that we can use. We even have an inverse t command or an inverse t program that could help us do the same thing. So we haven't needed this table. So the last table, though, is an interesting table. It's the chi-squared critical values table. Because there is no inverse chi-squared command on your calculator, this could be really quite helpful. So the degrees of freedom in our question are 9 degrees of freedom. So we want to go to this row of the table. And notice what the table is going to give us. It is going to give us this chi-squared value, or the critical value that corresponds with having a specific probability above it, and that probability is known as the tail probability. So that probability is what we are looking for up at the top. So what I'm interested in looking at is the column of 0.05 for the probability and 9 degrees of freedom. That corresponds to this critical value right here. So what this is telling me, at 16.92 for my chi-squared statistic with 9 degrees of freedom, the tail probability, the probability above it, is 0.05. That's exactly what you would want to communicate in this question. So again, these are combined together. So there are two components here that are combined into one. So in part D, you would have to mark and label that 16.92. I went ahead and shaded above it and labeled it at 0.05. So then also in these corresponding graphs, you would also have to shade the regions that correspond to simulated values that are at or above the corresponding 16.92. So starting here and above. So you just want to carefully shade over those or draw over those. So if you have done both of those correctly, it is essentially correct. If you only do part D or part E correctly, it's partially correct. And if you miss both of them, that would be incorrect. So lastly then, in part F of the question then, here is what's going on. So in part F of the question, an essentially correct answer identifies the correct distributions. So histogram 3, that should be identified as the sampling distribution that had the largest variance. Histogram 2 should then be identified as the sampling distribution from the population with the smallest variance. So that's the first thing that you needed to do. So that's a partially correct answer, but to get an essentially correct answer, you also have to go forward and justify why you chose those histograms. But that justification needs to be linked to the likelihood of rejecting the null hypothesis or not. So I tried to write these answers carefully for you. So if the variance in the population is larger, this test statistic will tend to yield larger values because it's going to have a larger numerator. So observing then that the regions, looking at the regions that we marked in part E, so it would be good to go back and refer to those, histogram 3 has more shaded area. So in other words here, this shaded area, those represent critical values at which we would be rejecting the null hypothesis. So thus, the values of the statistic are large enough to reject the null hypothesis in favor of HA. Those values are more frequent in histogram 3 because the shaded area is greater there. So on the flip side, looking at histogram 2, and again, I wrote my answers in parallel form, histogram 2 corresponds to the population with the smallest variance. So of course, if the population variance is smaller, this statistic is going to yield smaller values, but why is that important? Why does that link back to 3? So what that means is, if we observe the regions that were marked in 3, histogram 2 has the least shaded area. And that is because the frequency of the values that are large enough to reject the null hypothesis, they are least frequent in histogram 2 because this is the histogram that has the least amount of variance in the population that was used to create these simulated values. So Corresponding then, the histogram to the one that has the largest population variance, the histogram to the one that has the smallest variance, that gives you a partially correct answer. But then you have to link back to part E. And in part E, what you are doing is you are shading in the regions where the statistic is large enough to reject the null hypothesis. So your observations here also have to link back to this notion of rejecting the null hypothesis. That's part of the context of this question. So hope this has been helpful.